calculations involving weak acids. Let's remind ourselves of the equilibrium that we are dealing with. So we have any acid and we put it in water, we get dissociation to H3O plus X minus. Now obviously we do tend to just abbreviate that and ignore the H2O and just write it as H plus X minus. Now when we've had a strong acid, we have assumed that there is complete dissociation, and therefore if we know the concentration of H plus, we can just plug it straight into minus log to the base 10 of the hydrogen ion concentration and get the pH. Now we cannot do this with weak acids, because weak acids are only partially dissociated. And that means that we can't find out the concentration of H plus just from the concentration of the acid. We're going to have an additional step in there. So because we don't know the extent of the dissociation just from the values, say from 1 molar ethanoic acid, what we're going to have to do is to use a new constant that will tell us the extent of the dissociation. So if we're to write a Kc value for this, a Kc expression, then we're going to do concentration of products over reactants. So here is our Kc expression. Now, because there is lots of water around, then we can combine the Kc together with the H2O, and we can make our new constant, which is called Ka. This is the acid dissociation constant. All acids have acid dissociation constants, even strong ones. It's just that we only really use it in calculation for weak ones. So let's write Ka. Ka is H3O plus concentration of X minus multiplied over concentration of Hx. And because we're a bit lazy and we don't always acknowledge the fact that it's not just a proton, we do write this as concentration of H plus times the concentration of X minus over the concentration of Hx. So you need to be able to write these for any given acid, so you need to know which protons drop off and do the dissociation, but that's your general one for it. So let's have a look at what some of these values are. So if we have got ethanoic acid, then the Ka is 1.76 times 10 to the minus 5, and that's moles per dm cubed. Let's compare that to a different acid. Let's compare it to carbonic acid. And in that case, the Ka is 4.3 times 10 to the minus 7 mole per dm cubed. So just comparing those numbers, the carbonic acid has a much smaller Ka than the ethanoic acid. Think what that means in terms of this mathematical expression. That must mean that the top part of the Ka expression is smaller than it would have been if you were comparing it with the ethanoic acid. So a smaller Ka means a weaker acid. So in this case, ethanoic acid is a stronger acid than carbonic acid. So how do we use this when we're doing calculations of pH? I've written the equilibrium expression again to remind us. And we know that if we were to write Ka for this, then we would have concentration of H plus on the top times the concentration of X minus over the concentration of Hx. And say we had our value for this I'll just pick one out of my reference table. We'll have 1.8 times 10 to the minus 5. Okay, so a question could give you the concentration. So say we have got this value. So it's going to give us this value. That leaves us with the H plus and the X minus to deal with. And obviously the H plus is what we want to get to in order to do the next part of our calculation. So what we know here is that the concentration of H plus must equal the concentration of X minus, because they basically have the same molecule that's broken in half. So we must have exactly the same amount of H plus as we have of X minus. That means that we can do an approximation so that we can approximate that the Ka in this case is equivalent to the concentration of H plus squared over the concentration of Hx. So that means if we wanted to work out the concentration of H plus, then we could go to H plus squared is equal to Ka times concentration of Hx. And therefore, if you want the concentration of H plus, then we do the square root of Ka times the concentration of Hx. So let's look at an example of this. So in this, it's asked you to calculate the pH of a 0.002 mole per decimeter cube solution of ethanoic acid, and you've been given a Ka. So quite often the first question in an exam question is for you to write the Ka expression. So for ethanoic acid, it would be this. And therefore we can approximate 2 Ka is equal to the H plus squared over the concentration of the acid. So we are going to rearrange that and calculate the concentration of H plus as being equivalent to the square root of the Ka times the concentration of ethanoic acid. And then we're just going to plug some numbers in. I'm going to show a few steps in there. I know you have a tendency to just bung them all in your calculator and cross your fingers and hope for the best, but I'll do it out in all the steps. And let's just square root that answer. And that's given us 1.876 times 10 to the minus 4 moles per dm cubed. So pH now, minus log that, minus log answer. It's going to give us 3.73. Remember, 2 decimal places for this. We can do a mental check. Does this seem a sensible value for a weak acid? And it does. So we can probably move on from this.